Okay, so let's move on to the lecture today, which is about quantum measurement. Here it is. What is this quantum measurement problem? We have a problem in measuring. I mean, what do? You take the measuring tape, you stretch it across the table. Why would that be a problem? Okay, see, it sounds like a straightforward thingy, right? Okay, and here it is. Okay, it's the quantum measurement problem. These are the essentially the main points. How or whether wave function collapse occurs. Okay, I like the fact that they say whether, not just how, because if you say whether, you mean maybe it doesn't occur, or what are we trying to answer here? Okay, if it doesn't occur, then there's nothing to answer. Only if you have that how, then yes, you would try to answer how it happens. What caused it to happen. But if they say whether, are they saying that sometimes it doesn't happen? And we're going to get into what a wave function collapse means. Okay, but keep that in mind. Okay, that says the inability to observe such a collapse directly, okay, has given rise to different interpretations of quantum mechanics. What are we saying here? Okay, there's something very important. They're saying inability to observe. Okay, I thought mathematical physics harped upon observation. They say you must observe. And here these people are saying that we have no ability to observe, okay, the wave function collapse. So is this outside the bounds of science? Is that what they're saying? Because we have no way of testing the hypothesis, as they say. Okay, so keep that in mind as well. And then the other one, the different versions of these interpretations, right? Pose key sets of questions that each physical interpretation must answer. And that's what it comes down to. What these people have done is they've come up with all sorts of physical interpretations for this unobservable, this by its very nature, this unobservable phenomena, which they call the measurement problem, which means the wave function collapse. So they have no way of seeing it. They have no way of testing it. All they can do is describe. What do they describe? They describe what they can see, what they can take pictures of, maybe what they can simulate with their computers, but they can't see the mediators themselves. And so they're guessing. And no problem there. They can hypothesize, as it's called. They can theorize. They can say, look, I've got an idea how that could happen. That's no problem. The problem here is the irrational explanations you're going to hear next of how these people have answered this so-called wave function collapse. Okay, so here it goes. Here's well, first let's get to the measurement. What is a measurement? I mean, what are they talking about when they say we have a measurement problem? Okay, so what is a measurement? Well, here it is. Okay, and it sounds pretty much like the story of the Emperor's Clothes. I think they're trying to sell you a Whopper. Okay, with all this wave function collapse. It says the testing or manipulation of a physical system in order to yield a numerical result. So they're going to manipulate a system of some kind, okay, physical system, could be a table, a chair, right, in order to yield a numerical result. They say this table measures 1 meter, okay? But how do you measure something you can't see or touch? Does it make sense to go to the lab and measure that which you can't see or touch? What are you measuring? Are you just stretching your measuring tape across space? Nothing? Is that what you're doing? What are you measuring? The length of nothing? This is the issue. And so the predictions that quantum physics makes are in general probabilistic. Yeah, they're probabilistic because they're going to be doing math. They're not going to be doing science. They're not going to be doing physics. Okay, they're not going to have an explanation for you. What they're going to be doing is measuring speed, energy, mass, charge. They're going to measure parameters. Okay, and that's what they're going to call science. What is it really? It's mathematical physics, meaning mathematics. It has nothing to do with physics at all. Physics is explanation, math is description. What these people are going to do is give you a description, and the explanation that they're going to give you is just going to blow your mind. And here's the first one, okay? What's the first explanation they give for the wave function collapse? Well, here you see it. Came from these two fellows, primarily from Heisenberg, the guy on the right, lower right. It's the Copenhagen interpretation, and that's the most popular still today after almost 100 years of quantum mechanics. An irreversible process causes the decay of quantum coherence, okay, which imparts the classical behavior of what? Observation or measurement. They call those are classical behaviors. If you can measure something, you're doing something classically, okay? That's called a measurement. But if you're doing something in this world that you can't see, prove, or measure or whatever, well, then they're going to call it a quantum process. So we have the difference between, on the one hand, a classical process which you can measure, and these that you cannot measure. And that means get a numerical value that you can rely upon. Why? Because we're going to see that it's kind of fuzzy. It's a fuzzy because you're measuring according to them, right? Measuring a wave, okay? And a wave is kind of stretched out. It occupies lots of space. In fact, all the way to the edge of space-time, and it occupies the whole universe. They call it a field. They have all these words for it. But as soon as you take the measurement, that the one you're going to put down, well, it collapses the wave function and it turns into a ball, okay? And here, let me show you a little pretty picture of that, okay? Here's what they're talking about, okay? Here you have a wave, and it suddenly turns into what? A ball. That's what they're saying. That's what they say when they say it's a wave function collapse, okay? So what they're saying is something converts into something else. In this case, they have this elongated thing, and as soon as you take the measurement, what happens? Well, it collapses to a ball. And that's just an example, okay? So the question is, what is the process? It turns out that they don't explain the process for a specific reason, and the reason is that, you know, they cannot explain it. They cannot explain how that happens. And the other reason is that they're talking about math. They're talking about what you measure, and they're talking about equations. When they talking about when they talk about a wave function, they're talking about math. So they're saying the function collapses. Forget about the adjectives in front of it, wave, quantum wave. Forget about this adjective. It's a function. What do you mean the function collapses? Well, again, it's a probabilistic theory, so it deals with probabilities. And so they're doing math, and they use these terms which are of physics. When you talk about something collapsing, you're talking about something physical. You know, what collapses? Well, you can say the government collapses. Well, yeah, that's a concept, and that's using the word collapse with a concept, with an abstraction. You say the government collapsed, okay, or money collapsed. But when you use it with physical objects, then it's very clear. You say, well, you know, what collapsed was the building. That's a little different. Now you're talking about things. That has to do with physics. The other stuff, you know, has to do with either philosophy, if you're going to talk about reason, purpose, or talk about belief, opinion, you know, why you think the thing collapsed. That's religion. But we're going to do physics. We can't use the word collapse and apply it to a concept, an abstraction such as an equation, a function. What the hell does that mean? But see, they give you the notion that the reason they can't measure accurately the location of the particle is because the wave function collapsed. They're suggesting that, or more than that, they're actually telling you in your face, they're talking about something physical. They're saying there's this thing called a wave that's waving out there, and it collapses to a ball. That's the notion they want to give you. But, you know, when you put them against the wall, they say, well, it was the wave function. And what we mean by that is the function collapsed to a reading, to a value. So they're talking about abstractions, but they're using these physical terms. They give you the impression that they're talking about physics when they're not. They're talking about math. Okay, so that's extremely important to understand in this situation. Okay, and fortunately we have someone on the internet, and his name is Nick Lucid, and he runs a site known as the Crazy Asylum. The Crazy is the, what is it? The Physics Asylum, the Quantum Asylum, whatever he's called today. And that's Nick Lucid. He looks more or less like Curly of Three Stooges, so I like to call him Curly. And he says, what is actually waving? You know, he's talking about, again, this wave function collapse. He says, what is this wave that's waving? And he says, probability. He answers that question. What is waving is probability. What is waving is a function. Are we talking about physics? Or are we talking about math? How can you say that a function waves? I mean, you see the problem. We're talking about abstractions that are moving. And that is very scary, okay? Anyways, he continues, he says, remember, we're taking a trip down the Quantum Brick Road. Yeah, we're headed to Oz, okay, here. A wave is anything that has a back and forth shape. Now, what kind of shape is a back and forth? Form, shape, whatever. What is the outline of a back and forth? You see how they use these words? They want to apply a word of physics such as shape, and they want to apply it to what? To back and forth, which is a verb. You can't have the shape of running. What is the shape of flying? What is the shape of swimming? That's what this guy is saying. And they use these words, and it only confuses the dissertation because you don't know what they're talking about. Are they talking about physics? Or are they talking about math and abstraction? What are they talking about? What is a wave function collapse? Okay? So yes, while wave is a verb, he says it, okay, it is also a noun. Waves are things. How are waves things? The flag is a thing. What it does is wave. You can't say that a wave is a thing, but this is how these people talk, and it's pervaded the language completely. So this is how these people talk, and it is very confusing, especially to the layman out there who's not careful or tune into really what these people are into or what they're saying. Okay, they say, "Oh, that's over my head. That's nice to know. Science is so great," and they walk away and they never learned anything because these people talk this way. He continues to say, a mathematical function. He defines it as what? A relation between sets of numbers. Okay, so it's a relation. What is a relation? A concept. That's what a function is. A wave function is a function that looks wavy. Great. Wave function is wavy function. Great. Good definition. Again, these people never learned to define words. That's the problem. Quantum wave functions are a bit more abstract than that. More abstract than that, okay? I don't know. I don't know how much more abstract you can get than that. They're unobservable by definition. Okay, so here we have a wave function. They say there is something there. It's called a wave function. They're talking about a function, which he says is a verb, right? Or a wave that is a verb as well, right? And they're waving it, okay? But he says because, I guess, they're concepts, they're unobservable. Yeah, no kidding. All concepts are unobservable. So should we remove that from science because they claim that science is what you can observe, measure, test in the lab, and here they can't even touch it or observe it, see it? Is this outside the bounds of science? According to their own definitions, by the way. I'm not introducing my definition at this point. I'm using their own definition. They're not being consistent with their definitions. Okay? So the point is the quantum wave function isn't even completely real. He says that, not me, okay? It's not real. I thought physics dealt with what's real, what exists. Isn't that what physics is about? What exists? Isn't that what we're interested in understanding? What exists out there? What causes gravity? What causes electricity or magnetism? What exists out there that we can't see or touch or prove through observation or go to the lab so that we can see or touch it? This is not an issue where you go to the lab and run an experiment. You're not going to figure this out through an experiment. You got to sit back and visualize. You say, what could Mother Nature be using there to produce all these effects that we can't see or touch? We can't see or touch the mediators of these effects. That's what science is. That's explaining, giving me an explanation how the universe works. But to say that you're going to wave the wave function and that a wave function cannot be observed, yeah, no kidding. I have trouble always observing verbs. Usually I observe nouns. Okay, so he ends up his little dissertation saying the following. Instead of looking at the quantum wave function itself, we look at its probability density. My God, probability. That's what they look at. I hope you can see the probability density. In other words, these people are going to be doing math. So he says, so what's a quantum wave function? Okay, what is it? It's a mathematical entity, calls it an entity, that has no physical meaning. Those are his ending words. So what did we learn? Well, we learned that there's no such thing as a wave function. It doesn't exist. It's not an object. It's not a thing. But he calls it a thing. He calls it an entity. Okay? And what's more, he's going to wave it. And he says, well, because it's not just a wave. A wave is not just an object. A wave is also a noun, a thing, an object. So they're treating it, that's why they use the term mathematical physics, because the physics part is the object that they're going to use, and you're not supposed to take it literally. And then the math part is the description of, the equation that describes its motion. And that's the part they're interested in. They say, well, we're interested in this in math. We want to do equations so that we know how it moves. And some of that might have to do with technology. None of any of that has anything to do with physics. Physics is understanding how Mother Nature runs her shop and what mediator she uses to do that. You got to visualize the mechanism. For that, you got to introduce objects that you can't see or touch because you're going to use them to explain a mechanism to someone else. What the theories, what you have going through your mind, what you're visualizing. Okay, and yeah, you can put ghosts in there, and okay, that's your explanation. Fine. Someone might believe it, other people might not. Okay, and again, whether they believe or not, outside the bounds of science. But yeah. Anyways, here we have the second version of this wave function collapse. It's known as the many worlds interpretation. My God, if you thought the other one was crazy, this one beats it by a mile. It says there is only one wave function. Okay, the superposition of the entire universe. So they're saying there's only a single wave function. They're visualizing this as a field, I guess, that extends throughout space and time, space-time. Okay, so what is this field? Well, everywhere it's got all these vibrations. What are those vibrations? They're the waves. It's a single wave, but it's everywhere. Okay, and whenever you pinpoint one, you're going to measure. You're measuring only a piece of this monster, this web that extends throughout the universe. That's the notion they want to give you. The wave function never collapses, according to these people. They say it's constantly there. It doesn't collapse. So there is no measurement problem. So these guys are people who believe in the many worlds. They do not subscribe to the traditional Copenhagen interpretation, which is, the wave function collapses. These guys say, no, there is no wave function collapse or measurement problem. What happens is you have this monster, which is a bunch of waves that form the field, and whenever you measure, you're just measuring it locally. Okay, but what happens? It gets even worse, because it says all possible outcomes of quantum measurements are physically realized in some world or universe. I talked about Schrodinger's cat. Just briefly, let me illustrate it here. Here it is. Okay, I presented this the other day a couple of times already. That's Schrodinger's cat there, and for those of you who don't know the story, you put the cat in a box, and you have this. What is this poison? You can say it's some radioactive poison that's in a glass jar. And what happens? You break the glass with a hammer that's timed, and at some point, the glass breaks, and the radiation comes out, and supposedly it kills the cat. Now, you don't know if the cat is already dead in there, if that's already taken place or not. All you know is that the cat is either alive or dead because you haven't opened the box. Now you open the box, and they say, the quantum mathematicians say, the cat collapses to one of two states. Either he's dead or he's alive. That's essentially what they're doing with particles. Okay, so this is an analogy for the particle universe of quantum mechanics. Okay, what is the issue? Well, the issue with the multiverse theory, in other words, this many worlds, it's trying to incorporate general relativity, the notion that there are many worlds out there, many universes, and what happens is the cat actually lives in all these universes. He branches out in all of them, and in one universe he's dead, in another one he's alive, in another one he's standing up, in another one he's maybe half dead, half alive because he's maybe sleeping, waking up. So the cat, for every step he takes in his life, he branches off into these many universes, many worlds. Now, what sense can any of that make? Is this a rational explanation? These people study 10 years at the university, and this is what they come up with. They come up with the wave function collapse, the wave collapsing to a ball. We don't know what the process is, but it does so. And the other guys say, no, it doesn't really collapse. The wave or the particle or whatever that branches off into all these universes. And here it collapsed, and here it didn't collapse. Who knows what happened? But they say the wave function doesn't collapse because it covers the entire universe. You figure it out, what they're talking about. In fact, I wonder if they know what they're talking about. Okay, there's a couple more, and I'll go quickly through these. They're not so popular. And this one comes from the Broglie and Bohm theory. These two guys, essentially, and lots like them, Einstein among them, they were all wave theorists. And they're a little different than people like Bohr, and Heisenberg, who were more particle theorists. They believed more in the particle. And so it was really a fight between the particle theorists and the wave theorists, and the particle theorists won the day. And eventually they kind of merged it into this notion of field. They came up with a field theory of quantum mechanics. And they like that because it kind of unites general relativity, which is a field theory, together with quantum. And that's what they're trying to do today, somehow figure out how the equations from one discipline, general relativity, can match the ones from quantum mechanics. They're trying to get an equation that explains both sides. Okay, that's essentially what string theory is trying to do. But it says there is no actual collapse. These people don't believe in the collapse either. Okay, system description contains the wave function and also the position of the particle. This is kind of strange because, wave is motion, position is something static. And they say, who was it? Mr. Heisenberg said you cannot have both motion and position, the amount of motion, or you can't zero in how much motion there is if you know the position, and vice versa. If you know the motion, you do not know the position of the particle. And I always like to say it, synthesize it by saying, when the ball moves, it doesn't stand still, and when it stands still, it doesn't move. That's what the uncertainty principle essentially says. And so here we seem to have a contradiction because This guy is talking about these fellows, anyone who's a wave theorist in general within quantum. Okay, they try to fix this problem, saying, look, there's a difference between the wave and the position, and these people are saying we can have both. We can have our cake and eat it too. Okay, that's essentially what these people are saying, because they're saying there is no collapse. Okay, and therefore there is no measurement problem. Also, like all the guys said, role of the wave function is to generate the velocity field for the particle. Okay, and velocities are such that the probability distribution for the particle remains consistent with the predictions of orthodox quantum mechanics. These people are talking about probabilities, they're talking about predictions, they're talking about descriptions. They're not going to explain anything to you, even with this so-called theory. It's not a theory. It's a description. Theories are not descriptions, and descriptions are not theories. A theory is an explanation. These people had to turn their descriptions into theories. Why? Because they had to somehow make sure that everybody out there understood that mathematics is a synonym of science. Mathematics is a synonym of physics. Why? Because physics is how the world works, and they claim, hey, mathematics can give us a clue or tell us exactly how the universe works. That's their notion, their line of reasoning for how science works, how physics works, and of course how math fits into all this stuff. Okay, interaction with the environment during a measurement procedure separates the wave packets in configuration space, which is where apparent wave function collapse comes from. What interaction, I say? What is interacting? So far they have no physical object. How can it interact? All they have is functions. How can a function interact with anything? How can a wave interact? How can it bang against something? They don't have physical things. They don't do physics with things. Okay, and that's the first rule of physics. You need to have a thing. Okay, without a thing, you have nothing. Okay, that's the way I like to look at it. Okay, and one more, which was this. This is another interpretation. Okay, and it's the objective collapse model. Not necessary to go in any detail through this, because what they're saying is they modify Schrodinger's equation. That's math. It's got nothing to do with physics. Then they say they're talking about the behavior at the microscopic level. Okay, and again they're saying quantum object that is unmeasurably close to that given by the Schrodinger equation. Again, they're talking about numbers, functions, equations. They're talking about descriptions. They're not going to give you an explanation for what this objective collapse model, which is a theory according to them. What theory? You haven't explained anything. All you did is describe. It's like saying, I measured the table. Okay, so how much does it measure? Well, it measures 1 foot. It's a small table. Okay, and what have you explained? Is that science because you measured a table and you give a perfectly accurate reading? What the hell is that? Okay, it says for microscopic objects, the nonlinear modification becomes important and induces the collapse of the wave function. Again, collapse of the wave function. It's collapsing the function. They're trying to tell you that they're doing physics, that they're working with something real, some real object out there. When good old Nick told us just now that there is no such monster. Okay, and yeah, what is the mechanism? How does the wave function collapse? Please explain to me. Put it on the board. Show us a movie of how the wave function collapses. I want to see it. I want to see it. Keep your mouth shut. I just want to see the movie. That way I can see how it collapsed. What are they going to put? A function? A bunch of A's and B's, X, Y's, and Z's? The main difference of objective collapse models compared to the other approaches is that they make falsifiable predictions that differ from standard quantum mechanics. Yeah, falsifiable prediction. What is that? Falsifying is an opinion. For you, God is false. For this other fellow, God is truth. Who's right? Who falsified who? Falsification is an opinion, nothing more than an opinion. And they're falsifying predictions. That's even worse, because if you falsify a mechanism, you can say, well, let's go to the lab and find out. But these guys are talking about predictions. What are they talking about? Where the Scorpio is going to be in the sky someday, the sun or the moon? Are they talking about astrology? Is that what this is all about? What are my conclusions? Quantum measurement has to do with detecting the invisible and intangible. Can they detect the invisible and intangible? No, of course not. So there's no purpose in running any experiment in the lab, because you're not going to be able to touch or see what you're looking for. You got to define it and say, oh, this is what it is. Now you know what you're looking for. You say, I lost my wedding ring. Okay, what are you looking for? Well, I know what a wedding ring is. You look for a ring, you're looking at some little hole there, right? So you know what you're looking for. But when these people say, they're looking for something that is intangible and invisible, please draw it, so I know that I found it when I see it. I mean, how are you gonna deal with something that's intangible and invisible except through visualization, through imagining it and drawing what's in your brain for someone else so that they can see the same thing you saw. Okay. Okay, there are no observers in science, but quantum is saying that the mathematicians, okay, can't see or detect the invisible mediators. So does observation play a role in science? If it does, then we have to eliminate quantum, because in quantum they tell you right up front that they can't observe whatever they're studying in the lab. So is observation part of science or not? And then the mathematicians insist, in spite of this, right, in doing experiments to see and detect them, to see and detect what can't be seen or detected. And when you put them against the wall, they say, well, they continue to provide physical interpretations despite summarily dismissing all physical interpretations as philosophy. So you figure out, is that philosophy? Is telling me why a pen falls to the floor, is that philosophy or the mechanism, right? Or is that physics? And these people dismiss physical interpretations as philosophy. Then they give you a physical interpretation, the most idiotic, the most irrational one they can find. They tell you they cannot observe or see or detect it in any way. And then they say, come with me to the lab so you can see the experiment that I'm going to run to what? See and detect the unseeable, undetectable? So you figure it out if this quantum measurement is even a problem. Should we even pay any attention to quantum measurement? Does it have anything at all to do with physics?